Hello, hello. Total Development Lab back again with another video. And today we are going to go over the Hill Cipher. Now, this is just one in two videos where we explore ciphers and implement the algorithm in the Rust programming language. But today, let's just keep it simple and do a bit of an overview. So, a little bit about the cipher. The cipher is a classical polygraphic substitution cipher. It encrypts groups of letters simultaneously. It uses matrix multiplication to transform plain text. It relies on modular arithmetic, and it also introduces linear algebra concepts that appear throughout cryptography. So let's go over a little bit of the history. So the Hill cipher was developed by a mathematician, and his name was Lester S. Hill. It was published in 1929. And one of the earliest cryptographic systems explicitly based on linear algebra, and it was designed to encrypt blocks of characters instead of one character at a time. And it's historically important as an example of mathematics being applied directly to encryption. So, where it was used, the Hill cipher was primarily significant as a mathematical crypto system rather than a widely deployed military cipher. And today, it is commonly used for cryptographic education, linear algebra demonstrations, cybersecurity coursework, capture the flag challenges, and teaching block-based encryption concepts. So let's get started in the cipher. So first things first, we need to convert the letters of the alphabet to numbers. So with that being said, we start by mapping letters to numbers. So A would equal to 0, B would equal to 1, C 2, all the way down to Z being 25. Great. So now that we know that, let's do a quick example. So for the example help, as you can see here, this converted to numbers would essentially be H equaling 7. As we can see over here, H does equal 7. E would equal 4. E does equal 4. L would equal 11. L equals 11. And P would equal 15. Let's find P. P equals 15. Perfect. So that is our encoded example for a message. Great. So let's go over an example where we talk about the encryption key. So our key is essentially a convertible matrix, right? So we need to choose the size of the matrix to begin with. In this example here, we are just using a 2 by 2 matrix, but there's something that we need to note. The key matrix size will determine the size of each split of the message. So for example, if we used the message help, we need to split this message into size 2, right? So we need to have pairs of characters that are equal to the matrix size. This is an n by n matrix, right? That's what we mean by this. It's important that the key matrix size is the same as the message pair or message split length. So as we go over here, we see that for the secret message hi now, let's go over this an example. So for the secret message hi, we want to get the values of each character, right? So H would be 7 and I would be 8, right? So we then put these values into our vector. And this would be 7 goes first, and then 8, and 8 goes down here. And this is our p-value. And this, as you can see by our encryption algo, is what we multiply by our key, or k. And as you can see, our k is over here. Great. Let's move forward. So with our encryption example here, we have our k matrix, and we have our p message. So what we need to do now is take our algorithm and then perform the linear algebra, right? So what we need to do is say multiply our key by our pair. And how we do this is fairly simple. We take the first column or the first row here and multiply it by each respective value in the vector. So this would be 7 times 3 plus 8 times 3. And that equals 45. And then we do the same thing for the bottom row. So that's 7 times 2 plus 8 times 5. Better represent that. And that equals 54. Now, we take our values from our multiplication and apply the modulo 26 to each of the items in our vector. And that looks like this, right? So we say 45 mod 26, and that gives us a remainder of 19, as you can see here. And we do the same thing for 54. That gives us 2. So our encrypted ciphertext would essentially be 19 and 2. And as we know from our already converted encoded alphabet, these map to T and C, as you can see here. So our encrypted message hi turns into T and C. And this is what we can give to our friend or our secret message so nobody else can know what we're talking about. Now, how does the decryption work? So to decrypt, we need the inverse of the key matrix modulo 26. So as we just went over an example with the encryption, we need to go over the decryption now. And you can see they're fairly similar, but we just need the inverse here of our key matrix. And let's go over a note here. So not every matrix can be used as a Hill cipher key. So we need to be very cautious in what we use as our key. And the determinant of the matrix must have a modular inverse modulo 26. So with that being said, let's move forward. So why does this determinant matter, right? So since 9 and 26 are coprime, the determinants have a modular inverse. And how we calculate the determinant, right, is essentially we take 3 times 5 and 3 times 2. All right? That's how we grab our determinants. And then we get the greatest common denominator out of them, and then it equals 1. So therefore, the matrix can be inverted with modulo 26 and used for encryption and decryption. Wonderful. So let's move on. What are some strengths of this in Cipher? So the cipher encrypts multiple letters simultaneously. It hides single letter frequency patterns better than monoalphabetic substitution. And it also demonstrates block-based encryption. And it uses mathematical transformations rather than simple substitution tables. And it's an excellent introduction to cryptographic linear algebra. So as we usually go over some strengths, we need to go over some weaknesses. So the weaknesses of this cipher is that it's quite vulnerable to known plaintext attacks. The linear transformations can be mathematically recovered, and the key matrices must meet specific invertibility requirements. It also provides no protection against modern cryptanalysis. And it's honestly not secure for real world data. So, what's the real world relevance of this cipher? So, the Hill cipher itself is obsolete, but the underlying concept remains highly relevant. The block-based transformation, the vectors, the matrices, the modular arithmetic, the invertible transformations, and the key dependent mathematical operations are all useful ideas, right? And it gives us a conceptual bridge toward modern cryptographic systems. Now, in our next video, we will be implementing this algorithm or cipher in the programming language Rust. So stay tuned for that, and I will see you in the next one. But until then, take care and have a good one.